So now let us work out some examples. Start with water. What do you have? Wait, let me hear from the gentleman in the faraway benches. Yeah, tell me. Do you have a point of inversion? No. Do I have an axis of symmetry, simple axis? Yes, you all agree? Where is it? Here. And it's a C2 axis. Okay. Any other axis? No. Achha. Now let us look for planes. I think you are going to think that I am stupid if I even ask you if there is a vertical plane of, if there is a horizontal plane of symmetry. Obviously there isn't, so I won't ask that question. Do we have vertical plane of symmetry? Yes. Where are they? This is one, the molecular plane, and this is one, perpendicular to the molecular plane. Sigma v's. Go back. This is easy to understand. And now think of a plane that is perpendicular to the molecular plane. So this is how I have drawn it. I don't know whether it's easy to see or difficult to see. It's a plane that is perpendicular to the plane of the paper or the projection, whatever it is. So I call the first one sigma v and I call the second one sigma v dash. And here, even for this very simple molecule, I want to make a point. The point is that these two sigma v's that I have drawn, they are not equivalent to each other. Will you agree with me on that? So I call them sigma v and sigma v dash. I don't call both of them sigma v's. They are not equivalent to each other. Why do I say they are not equivalent to each other? There are two ways of approaching that question. First of all, what happens when I apply sigma v? When I apply sigma v, what is it that happens to the molecule? It remains an indistinguishable configuration, I agree. But think of the atoms. Let us call this atom A, let us call this atom B. If you apply sigma v, rotation with respect to, reflection with respect to sigma v, then HA and HB remain in their place, right? Only the upper lobe of HA goes below the plane, the lower lobe of HA comes above the plane. Same is true for B. Are we okay with that? This is the plane. Whenever I teach symmetry, I always wish that I had more fingers on each hand and maybe 2-3 hands more. But unfortunately, I don't, so I will have to depend upon your imagination. So, better switch to principal axis of symmetry rather than horizontal plane. I was lying down. Okay, this is your water molecule and this is the plane waving at you, right? What happens to this atom? Does it change place with the reflection? No. What about this atom? No. What about this atom? No. Now, if I think of the other plane, sigma v dash, then what happens? If I reflect, then this atom will go there, that atom will come here, right? There is an interchange of atoms, right? So even though both the planes leave the molecule in indistinguishable configurations, their actions are not one and the same. Sigma v does not cause a change in the position of any atom. Sigma v dash causes an interchange of the hydrogen atoms. Okay, their effects are different. And as you will see, whether the atoms move or not is going to become very important in later discussion. Maybe we don't discuss that in this course unless we talk about vibration, but we'll see about that. Okay, so you will agree with me now that sigma v and sigma v dash don't exactly do the same thing to the molecule. So they are not equivalent planes. Another way of checking it is this. What is the axis that we have in the molecule? C2. if I apply C2, does sigma V get converted into sigma V dashed? If I apply C2, now forget about the molecule, only think of this line, the axis, and the two planes. If I apply C2, C2 means what? 180 degree rotation. This is the plane, this is C2, right? If I rotate, then what will happen? The plane will remain the same plane. It is just that my hand, my wrist will not allow my hand to go that much. But it will remain in the same plane, right? And the perpendicular plane will also remain perpendicular. These two planes will never interchange. You see where the axis is? The axis is at the intersection of the two planes, isn't it? Right? The axis is at the intersection of the two planes. The two planes do not get transformed to each other by application of the only other symmetry operation that is there in the molecule C2. Okay? So, we have seen an example of non-equivalent planes of symmetry. Now, let us see an example of equivalent planes of symmetry. Okay, we will do this and we will come back. We have digressed a little bit. We actually wanted to give the name to water molecule, but anyway, let us finish this discussion and then we will come back. This is the structure of ammonia, and I hope you can see it in the 3 dimensions. One plane in the one bond in the plane of the paper, one bond pointing towards you menacingly. The third bond is scared of you, it is running away behind the plane, right? Now see, you told me that there is a principal axis of symmetry here. There is an axis of symmetry. What is it? C3. Where is your axis? This is the axis. What are the other elements of symmetry here? Sigma V. Where is sigma V? Yes. Plane containing the NH bond and the vertical axis, of course. So, I can draw it like this. This is one plane. This is another plane. I hope you get the orientation. It is along that bond that was pointing towards you, and this is a third plane, right? Like 3 blades of a fan. Alright. Now see, what does each plane do? Let us take this sigma V, let us call this sigma V. You agree that it is a vertical plane of symmetry, right? That it contains the principal axis of symmetry, the only axis of symmetry. So now let us call this sigma V and start work with that. What does that sigma V do to the atoms? Upon operation of sigma V, okay, let us name them also. I will call them HA, HB, HC. Upon application of this sigma V, first of all, the nitrogen does not change place, right? What about HA? Does HA change place? No. What about HB and HC? They change places, right? So that is the action of HA, sigma V. Now this one, tentatively I will call it sigma V only. What does that plane do? Will you agree with me that it leaves nitrogen and HB in their positions and cause an interchange of HA and HC, right? And the third plane, nitrogen and HC remain in their places, HA and HB interchange places, right? So see, the 3 planes have similar kind of action. Nitrogen and the hydrogen contained in the plane would not move. The other 2 hydrogen atoms would interchange places. That is the name of the game, right? So this all the three planes then are identical. Will you agree with me? I am sorry, they are equivalent. You should not say identical. They are equivalent planes. So I do not have the compulsion of writing sigma v and sigma v dashed anymore. They behave similarly. So I can call them sigma v. Okay. So that was the first definition. Let's look at the second definition. This here is your C3 axis, you told me. Now if you perform C3 axis, will you agree with me that the three planes interchange places? Remember what happened in water? You applied C2 and the two planes did not interchange places. Sigma v remained sigma v dash remained sigma v dashed. Here however, the three sigma v's get interchanged among each other upon application of C3. So there is another element outside the set which causes an interchange of the members of this set. That is the second definition of equivalence. Got it, Mihak? Huh? Sure? Okay. So I don't have to call them sigma v dash, sigma v double dash, ABC, nothing. Sigma v is good enough. They are indistinguishable. Okay. So this is a very important difference between equivalent and non-equivalent symmetry elements. All right. Now see, let us. I can see, but you cannot even see the flow chart now, isn't it? Even looking at, without looking at the flow chart, I think it's very easy for you to tell me the symmetry point group of ammonia. So the C3 principal axis, and the only other thing that is there is a vertical plane of symmetry. So it has to be C3V. Right? What about water? There is C2 and sigma v dashed are different, but it looks somewhat foolish if I call it C2VV dashed. There is no provision for that in your flow chart. So we are content calling it C2V. All right? Okay. Now, instead of me drawing bad diagrams, since you have this projection facility, I think it makes sense to show you the book right away. Okay. Next molecule we want to talk about is hydrogen peroxide. Can you see this clearly? Is it big enough? Can you see this? All right, and you know the structure of H2O2, right? It's non-planar. What are the axes of symmetry or elements of symmetry that are there? Unfortunately, the answer is given. There is one problem of showing you the book, right? The only thing you have is C2 axis. One bond is like this, one bond is another like this. Okay, so you take something in the middle, perpendicular. You turn, then the two bond gets interchanged. Okay. So what will be the point group? C? C6? C2. There is no C6 here. Fine. So maybe now I will cover some of these. What about this? This molecule. How do I not cover that and cover this? Yeah, there you are. Do you see the S4 axis? Huh? You turn by 90 degrees, what will happen? This will come, will it come here? Just turn by 90 degrees. What will the molecule look like? with respect to this axis here, if you turn by 90 degrees, then what kind of a structure will it be? This is what the molecule is, right? Let me name them. A, B, C, D. The bond is between A and B and C and D. Okay. If you turn by 90 degrees with respect to this axis, what will happen? In place of B, you will have A, right? In place of C, you will have B. In place of D, you will have C. In place of A, you will have D. And don't forget, the bond is between A and B and C and D. So, the molecule is turned by 90 degrees, and what you have is not an indistinguishable configuration, right? So, you could do that with the other bonds as well. And then what you see is, if you now, after turning by 90 degrees, if you reflect with respect to this plane during the midpoints, then you will get back the same kind of molecule. That is S4 for you. Let me see if I can draw it. You start from here. Turn by 90 degrees, so C4 operation, what do you get? What am I doing? Well, that's what it is. And now if you deflect, then what happens? If you reflect along a plane that is perpendicular to the axis, then again this will come up, this will come up. So earlier you had a bond in this orientation, again you have a bond in the same orientation. I wish I had got the model, it's very easy to see in the model. Okay, so this is an S4 axis. Alright. Let's move to an interesting example, and let me draw it actually. Okay, you know the structure of ferrocene? So what does ferrocene look like if you look down from the top? You see a 5-membered ring, not looking very good here, and you see another 5-membered ring, like this, right? And they are eclipsed. Okay, now it is very easy to figure out. Do you see the C5 axis of symmetry? C5 is not very difficult to see. This is C5 axis of symmetry, right? Both the rings are 5-membered. So if you turn by 2 pi by 5, you get back an indistinguishable configuration. Are we all okay with this? Are we all on the same page? Any other axis of symmetry? SN, S10. Yeah, the C5 axis of symmetry is also S10 axis of symmetry, right? Because then this carbon atom will come here and then get reflected upon this. Okay? Other than that, any simple axis of symmetry. First of all, the C2 has to pass through the iron, right? Let us first agree upon that. In ferrocene, what is it? Fe2 plus or Fe3 plus? or Fe0? 2 plus, right? Ferrocene. So, any C2 axis must pass through the ferrous ion. Okay, and any axis that passes through the ferrous ion, what will it do? It is going to interconvert the two rings. Right? It's important to understand that. So, this is ferrocene, right? Anything that can do this is going to be a C2 axis. Isn't it? This is ferrocene. You need an axis through this, which will give you something like that. Now, draw the structure and see if you can figure it out. And this is a little better than what I drew earlier. Do you see C2? These are the two rings, right? Iron is exactly in the middle. So, if you want the two rings to interconvert, then it must be something like this, right? Parallel to both the planes and right at the center. So, it must go through iron. The question is, at which angle? Of course, perpendicular to C5. I said that already. But even perpendicular to C5, you can have infinite number of lines. Right? So, now I am talking about this orientation.
Parallel to any one of the lines.
Which lines?
Any one of the line of the pentagon. Perpendicular to any one of the bonds. So, it should bisect the bond and pass through one of the parallel.
Okay, I will take that. Let me not draw it. Will you agree with me that that is C2? I wish I had a pen of another color. Let us look at it point by point, then only we will understand, okay? Yeah. This is one way of making a small diagram look big, fortunately. Let us name them A, B, C, D, E, F, G, H, I, J. I hope you can read that. Now see, when I turn with respect to this axis, don't forget where the axis is. Axis is equidistant from the two rings. It goes right through the ferrous ion and it is perpendicular to the C5 axis. Now if I rotate by 180 degrees, what I am saying is A and G should interchange position right here. Cannot see no matter where I write it, I have been over enthusiastic with the zooming. A and G would change places. Will you agree with me? A and G will change places. Huh? The angular disposition is exactly between, if I take the center and if I take projections in the middle, the angular disposition is exactly in between the two lines, right? So, A and G would interchange places. B and F would interchange places. C and I cannot even read, it's H. C and H would interchange places. Is it C or is it E? Sorry. A, B, C, D, E. E and H would interchange places. Do you see that? Huh? And you can work out the correlation for every atom. Let us take the simpler case of luthanosine. Luthanosine is very simple. In luthanosine, you have eclipsed 5-membered rings. I just draw these two sides, you can figure out, right? They are on top of each other. Now see, what do you have? You have C5. right? Do you have any other axis? C2. In this case, C2 is very easy to understand. C2 would be like this. But still, don't forget that this C2 is not on any of those planes. Even this C2 goes through the ferrous ion and is perpendicular to the C5 axis. Are you all okay with that? Your Anchal, right? Okay. So the C2 passes through the ferrous ion. It's not on any of the any of these rings and it's perpendicular to C5. How many such C2s are there? 5. Very easy to figure out. Okay, I'll not risk drawing another one. I think you can understand that there are 5. Okay, what else is there? Which plane? So first, which plane do you look for? Horizontal. Do you have horizontal plane of symmetry? Yes. Right, so we don't have to look any further. For the nomenclature at least, we are done. So what will it be? C5H? C or D? It will be D because you said there are 5 perpendicular C2 axes. 5 C2 axes perpendicular to the principal axis, right? So little more than C is D. So this is D5H. That was easy. Now what I am doing is, this is how the planes were. I am now turning them just a little. Okay. That is the case in ferrocene. This one. Right. That is the case in ferrocene. Now, what are the symmetry elements that will survive and what are the symmetry elements that will be destroyed? Let us think like that. C5 will still survive, right? Because C5, see, C5 is for the individual rings. Okay, the 2 rings don't talk. They don't get mixed by C5. They don't care, right? So C5 will still be there. Horizontal plane goes. Right, you agree with that? Horizontal plane cannot be there anymore because you turned a little bit, right? So that sigma is that was there will no longer survive. Agree with that or not? Because vertices are not on top of each other, isn't it? Right? So sigma h is gone. What about C2? Now let us ask the question. Is C2 there or is C2 not there? Now let us think like this. Earlier Ruthenocene, A, B, C, D, E, and bottom of A you had, I will call them 1, 2, 3, 4, 5. Right? The carbon atoms. The top 5 are A to E, the bottom 5 are 1 to 5. When you apply C2, what happens? Where does A go? And over Ruthenocene, the bottom one, the easier one, D5H. You apply C2. Where does A go? Okay, good question. This C2. A remains where it is? No. A and 1 interchange. Don't forget where the C2 axis is. The C2 axis is not on any of the planes. The C2 axis goes through the ferrous ion that is there, equidistant from both the planes, perpendicular, parallel to them. So A and 1 will interchange, is that right? Then B and 5, not B and 2, right? B and 5, E and 2, right? Then C and 4, D and 3, nothing else is left. Do you all agree? Now what I have done is I have turned just a little. This is your A, B, C, D, E, and let us say this is 1, 2, 3, 4, 5. So, by how much have I turned one ring with respect to the other? 36, right? I'm going from ruthenocin to ferrocin. What is the angular twist I have given? Keeping one fixed, by how much have I rotated the other one? 360 by 10. Right? Well, if you give 360 by 5, once again you will have ruthenocin kind of structure. Okay? You have rotated by 36 degree. Okay? Now, let us say I turn this C2 axis by 18 degrees. Half of 36. Okay, where will it go? Like this, isn't it? I'm sorry? It is going to the center. I mean, that's just bad drawing.
So there are 4 atoms on one side and there are 6 on the other.
4 atoms on one side.
4 atoms on one side of the C2 and 6 on the other.
Let's see, 1, 1,
Oh, like pass the point.
2,
A and 1,
2,
D and 3.
3, 3,
Between D and 3. It should be between D and 3.
between D and 3. Yeah, I got it wrong. Yeah, you're right. Between D and 3. Now it's perfect, right? Now you see the same A1 kind of correspondence is there. Okay? So C2 survive, even if you give a twist. It is just that unless the two pentagons are really regular, it is very difficult to draw that line. Okay? When we see it using the model, I think you will see it much better. But it's also important to try to develop the vision without the model. So the 5 C2s survive. Okay? C5 survives. Sigma H is gone. What about the planes? Are the planes there or are they gone? Vertical planes? Vertical plane will be something like this, isn't it? Is it there or is it not there? It is still there. It's just that you don't call them vertical planes anymore. These perpendicular C2s are there and the vertical plane would bisect the angle between them. So you call them dihedral planes. Right? So what do we have here? Principal axis of symmetry is C5. You have 5 C2s perpendicular to C5. So that makes the name D5. You don't have horizontal plane. So if you look for dihedral plane, so it is D5D. Alright? Fine?